Welcome again. Today on Chem in 3, we look at 3 types of intermolecular forces: London dispersion forces, dipole-dipole forces, and hydrogen bonding. Looking specifically at this application, the deduction of the types of intermolecular force present in substances based on their molecular formula. So let's take a look at hydrogen, for example. Hydrogen molecule is made up of 2 hydrogen atoms. But as we look at intermolecular forces, we're not concerned about the bonding inside of a hydrogen atom or an intramolecular force, but we're looking at an intermolecular force between one hydrogen molecule and another hydrogen molecule. And these shared electrons here in this hydrogen molecule, these 2 shared electrons at some point in time can actually be closer to one of the hydrogen atoms than they might be to the other one. And when this happens, we say that a dipole exists. And this side of the hydrogen atom that has more electrons, a higher electron density, becomes negative, and then this side becomes positive, having a small positive charge, delta positive and delta negative. And then on this side, this has the power to induce a dipole on this side, making this side positive as electrons get repelled over to this side, and this side becoming negative. This very weak intermolecular force, or London dispersion force, is not a permanent state, and at other points in time, these electrons can shift toward this side, and these electrons can shift toward this side. So the dipole is in a dynamic state, continuously moving around as the electrons move to different positions. And this is the weakest of the intermolecular forces. Next we consider Br2, which, like H2, has London dispersion forces, 2 bromine atoms making up a bromine molecule, here and here, and bromine molecules can be associated in the same way as these hydrogens were associated by London dispersion forces. But if we were to compare Br2 to an interhalogen, ICl, then we can see a different situation, because chlorine is a highly electronegative atom, much more electronegative than iodine, which means that the shared electrons in this covalent bond would be kept much closer to chlorine than they would to iodine. And this would be a permanent state, not a state of continuous movement, because chlorine is much more electronegative. So in this case, a permanent dipole exists, and the interaction between one ICl molecule and another ICl molecule would lead to a much stronger bond between molecules of ICl as opposed to molecules of Br2. And this leads to a significant difference in the melting points and the boiling points of Br2 as opposed to ICl, even though they both have a very similar relative molecular mass. And finally, the strongest of the intermolecular forces is hydrogen bonding. Hydrogen bonding is very much an extreme case of the permanent dipole, where you have highly electronegative elements like oxygen and fluorine and nitrogen attached to hydrogens. And these 3 highly electronegative elements lead to the formation of very polar molecules, like in the case of the water molecule, very polar molecule. The small negative charge on the oxygen, which holds on to the electrons in this covalent bond, associates with this hydrogen. The hydrogen actually attracted to the lone pair on the oxygen. This type of bond, indicated here by these 3 lines, is the hydrogen bond. And hydrogen bonding, we can say, is reserved, or the term hydrogen bonding is reserved for HF and H3 and H2O. And if these were to bond with other polar molecules, then that too would be hydrogen bonding. Finally, one more important point to note is that these 2 types of intermolecular forces are sometimes referred to as van der Waals forces. Now I would like you to take a look at these questions.